Hello everyone, my name is Tomasz Lewandowski. This presentation is about using GNSS raw measurements on Android devices. Using GNSS raw measurements may lead to a better location performance in mass market applications. Here we have a high-level overview of this presentation. At the very beginning, there will be a short introduction to the Global Navigation Satellite Systems, GNSS. It will include information about GNSS signals and reference times. Then we will discuss about what is needed for a PVT. PVT stands for Position, Velocity, and Time. With the next slides, we will try to answer the question, what are the raw measurements? Then we will explain how to convert raw measurements into GNSS measurements like pseudoranges and Doppler. After that, we will take a look into ambiguity resolution. Then we will present apps which can be used for raw measurements collection. We will check algorithms and code which can be used for GNSS measurement generation. And finally, we will go through the data processing in the RTK-lib. After that, we will explain how to perform in-field raw measurements collection and how to generate GNSS measurements out of the collected data. There are currently 4 GNSS constellations: GPS, developed by USA, GLONASS, developed by Russia, Beidou, developed by China, and Galileo, developed by Europe. They are complemented by several regional GNSS and augmentation systems. The GNSS satellites continuously transmit navigation signals in 2 or more frequencies in L-band. Signals which are currently used by mass-market devices are L1 and L5. This slide presents a GNSS signal plan for Galileo, GPS, GLONASS, and Beidou. L1 signals are highlighted on blue and L5 signals on red. GNSS is mainly known for its positioning capabilities. However, it is also a source of precise time. Each GNSS uses its own reference time. Relationships between reference times are known. Bias between all GNSS system times and Coordinated Universal Time, UTC, can be computed. Usually, multi-GNSS receivers implement only one clock based on one reference time. By multi-GNSS receivers, we understand the ones which are capable to use the signals from different GNSS constellations. Receivers need to know the relationships between reference times. In addition, clock corrections are computed by each system and are broadcasted in the navigation message. Figure on the left presents time difference between reference times. Table on the right contains relationships between reference times. These relationships between reference times are needed for the generation of pseudoranges using raw measurements. What is needed for APVT computation? Pseudoranges and satellites' positions are needed in order to compute a user position. Pseudorange is a distance measurement between the user's receiver antenna and the satellite position. Satellite position is computed by each GNSS system and then it is broadcasted in the navigation message. It may be also obtained by third means, for example by using assisted data. In order to compute a PVT solution, receiver needs at least 4 pseudoranges. They are needed in order to resolve 4 unknowns: X, Y, and Z coordinates and the clock bias. Clock bias is a time difference between the receiver time and the GNSS system time. The same bias applies for the entire number of satellites of each constellation. In May 2016, Google announced the availability of GNSS raw measurements from Android 7. On this slide, a generic block diagram of a GNSS receiver is presented. The RF block, the left side of the diagram, includes the antenna and the front end, which are required for analog signal processing. It can also include a low-noise amplifier, filters, and an intermediate frequency down conversion. The final element in the block is the analog-to-digital converter, ADC. In a smartphone, the baseband and PVT processing blocks, right side of the diagram, are software-based signal processing units that are designed to operate on a general-purpose hardware. The baseband processing is responsible for acquiring and tracking of the GNSS signals and decoding the navigation messages. Assisted data, external information, can be provided to reduce time to first fix. The baseband processing block provides the raw data to the PVT block, which then computes the receiver's PVT. This process benefits from augmentation data, for example EGNOS, or accelerometers. This leads to improved accuracy and availability in harsh environments. It is important to highlight that the raw measurements take place before the pseudorange generation. Picture on the left presents a location API in Android API level 24. Table on the right shows relationships between raw and GNSS measurements. The received satellite time and RX time are needed to compute the pseudorange. RX time stands for receiver time. Clock bias can be considered as optional. The accumulated data range is directly the carrier phase. Pseudorange rate is needed to compute the Doppler. On the next few slides, we will see how to compute pseudoranges. The construction of the pseudoranges is based on a time difference between the received time, measurement time, and the transmitted time. TTX is the received GNSS satellite time at the measurement time. It is the received satellite time provided by the Android raw measurements. It depends on the constellation and therefore is provided for each GNSS system. Depending on the tracking status, it can be ambiguous. TRX is the time when the signal arrives to the receiver or the measurement time. It is based on the receiver clock. It must be in the same reference time system as TTX. TTX is provided by Android, received SV time nanos. The valid range of received SV time nanos depends on the tracking status. The receiver needs to synchronize with the satellite transmitted signal. Picture on the left presents a synchronization with the CA code. If the receiver is only synchronized with the CA code, the valid range of the transmitted time is from 0 to 1 millisecond, making the computation of the travel time ambiguous. To solve this time ambiguity, the receiver can exploit the navigation message structure. Picture on the right shows the different synchronization stages required by the receiver to obtain the satellite time. Ranges bigger than the propagation time can be used for the unambiguous pseudorange generation. For each constellation, they are highlighted in the table on red. TTX is directly provided by Android, so the main task is to compute TRX. The receiver only has its internal hardware clock value, which is time nanos in Android. At the beginning, the receiver has no information about the GNSS time. In other words, the receiver clock is not synchronized with any GNSS system time. The receiver initial time could be when the receiver is turned on. For example, Galileo system time is running since 1999 and the receiver time is running since the receiver is turned on. What is the time difference between the receiver clock and the GNSS time? It is the clock bias, full bias nanos in Android. Here we have a way of computing TRX from Google. TRX is computed in a way that it includes receiver clock drift since the first epoch. Pseudoranges are needed for PVT, but clock bias from PVT is needed for pseudorange generation. Let's use a different approach and roughly synchronize the receiver clock with the GNSS system time. We can assume a standard propagation time between the GNSS satellites and the receiver. A standard value between 65 and 85 milliseconds is usually assumed. The receiver clock is initialized based on the first measurement and based on the propagation delay. On this slide, we have a way of computing pseudoranges for GPS, Galileo, and GLONASS. How to generate Doppler? Doppler can be generated using the rate of the pseudorange rate meters per second in Android. Using a given equation, we can compute the Doppler. Pseudoranges can be ambiguous. Figure on the left shows a jump of 4 milliseconds, Galileo E1c called length. After some epochs, the pseudorange goes back to the right value. During the jump epochs, the measurements can affect the positioning accuracy. Plot on the right presents a possible error on a PVT. How to correct the pseudoranges? In order to identify pseudorange with ambiguity, we can compute the difference between two consecutive pseudoranges. A value around 4, absolute value, indicates a jump in the pseudorange. The last step is to correct the measurements. Figure on the left presents pseudorange with ambiguity. Plot in the middle shows differences between two consecutive pseudoranges. Picture on the right depicts corrected pseudorange. On this slide, we have some information about Airbus GNSS Data Logger. It's an Android app which was developed by Airbus. This app can be used for raw measurements collection. App is available in additional resources. Here we have 3 other satellite navigation apps. GPS Test and Geo++ Trinex Logger are available on Google Play Store. There is also GNSS Logger, which is available under the given link. Before we start processing the collected data, it is important to remember about the possibility to cut the files, for example, by selecting a particular constellation. In that way, we will have smaller files and the processing will be faster. Let's check how to compute pseudoranges based on the raw measurements. On this slide, we have a set of equations which can be used for pseudoranges computation. There is also a screenshot from a worksheet. Green frame indicates output from Airbus GNSS data collector. Basically, it is a part of the MEAS file. Orange frame shows the computed results. Let's go through the equations. Speed of light is a constant value. Week seconds is also a constant value. It is the number of seconds in 1 week. Week number is a GPS week number. Week number nanos is a week number expressed in nanoseconds. TTX nanos is the received GNSS satellite time at the measurement time. It is expressed in nanoseconds and is equal to received SV time nanos. TRX nanos is the time when the signal arrives to the receiver or the measurement time. It is expressed in nanoseconds. TRX seconds and TTX seconds are expressed in seconds. PR seconds is a pseudo-range expressed in seconds. PR kilometers is a pseudo-range expressed in kilometers. Please note that worksheet is used for illustration only. In a worksheet, precision of the results may be lost due to the large numbers. Here we have a part of the MATLAB code which is available in additional resources. I'm not going to explain it since we are already familiar with those equations. Now we will have a few slides on how to perform RTK positioning. Xiaomi Mi 8 and Geo++ Rhinex logger were used for the data collection. Data collection was performed in Germany in a Munich area. Picture on the right presents a snippet from the collected Rhinex file. Rhinex stands for Receiver Independent Exchange Format. Collected file is available in the additional resources. To perform the processing, we need also Rhinex observation and navigation files from the reference station. Such data is available under the given link. Screenshots which are present on the slide explain the Rhinex files naming convention. FileZilla, picture on the left, can be used for browsing and downloading the data. For our processing, we are going to use Rhinex observation file from Oberpfaffenhofen and Rhinex navigation file from Leipzig. Pictures on the right show where both stations are located. By using the given link, a location of other IGS stations can be checked. IGS stands for International GNSS Service. For processing, we are going to use RTKlib. It is an open source program package for standard and precise GNSS positioning. All the input files which are needed for the processing are available in the additional resources. In additional resources, in GNSS Tools section, there is also a link to the RTKlib. In order to follow closer the next slides, I encourage you to download the RTKlib and to perform the processing steps by yourself. For the processing, we need to provide Rhinex observation file from the smartphone and Rhinex observation and navigation files from the reference station. Let's click Options in order to configure our processing. We are going to perform single point positioning and static RTK. RTK stands for real-time kinematic. Picture on this slide presents options for the first bookmark. Here we have settings for another bookmarks. Once everything is configured, just click OK. Once everything is set, we can start the processing. To do so, click Execute button. Results are saved to an output file. Snippet from the output file is presented on the right. In order to visualize the results, click Plot. On this slide, we have plots for both processings. Please note that for single point positioning, scale is 2 meters, and for the RTK, it is 1 centimeter. To conclude, we can say that by using positioning techniques, like RTK, we can obtain much more accurate position. There are also online services which can be used for the data processing. For example, JSON from RawKubun and Skylark from SwiftNav. Let's perform in-field raw measurements collection. What do we need for that? We need Android smartphone and Airbus GNSS data collector, which is available in additional resources. Then, we need to perform the following steps. At first, we need to install Airbus GNSS data collector on the Android smartphone. After that, we need to configure the app as it is presented on the right. The last step is to go outside, enable location on the smartphone, open Airbus GNSS data collector, and record the data. In case you don't have a possibility to collect the data by yourself, don't worry. In the additional resources there is a sample MEAS file which contains raw measurements. Let's generate GNSS measurements and more precisely pseudo-ranges. What do we need for that? We need data collected with Airbus GNSS data collector, MEAS file, or a sample file which is available in the additional resources. Moreover, we need a computer with MATLAB. The last thing which is needed is a processing script which is available in the additional resources. Once we have everything, we need to perform the following steps. At first, we need to transfer the data collected with Airbus GNSS data collector from the smartphone to the computer. Once we are done with it, we can directly process the data. Finally, let's answer the following question. In which range pseudo-ranges should be? Please check the values of the computed pseudo-ranges. Are all the computed pseudo-ranges in the expected range? I would like to say thank you to Moises Navarro Gallardo who contributed to this presentation. Some additional resources are also available. There is Airbus GNSS data collector, which can be used for in-field raw data collection. App has an expiration date, which is set to the 30th of April 2020. Moreover, there is a MATLAB script which reads MEAS file and computes pseudo-ranges. MEAS file is one of the output files from Airbus GNSS data collector. We have also a sample MEAS file which contains raw measurements collected with Xiaomi Mi 8 during a static test which was conducted on the 9th of August 2019. In addition, we have three files which were used for the processing with RTK-lib software. First of them is a Rhinex observation file collected with Xiaomi Mi 8 and Geo++ Rhinex logger. Second one is a Rhinex observation file from the IGS reference station. The last one is a Rhinex navigation file from the IGS reference station. Here we have a list of additional resources. They are split into three groups: general information about satellite navigation, positioning with mass market devices, and GNSS tools. I encourage you to check these materials. That is the last slide of my presentation. I hope that you enjoyed it. Thank you very much for your time.